How to think in parallel. Not just faster, not just bigger, but in a way that feels disturbingly close to how humans wrestle with hard problems, trying different ideas at once before locking in on the best answer. They call it Parallel R1, and it comes from Tencent's AI lab in Seattle with help from several top universities. And trust me, once you hear how it works, you'll see why people in the AI world are both excited and unsettled by what this means. Let's start with the big picture. Normally, when an AI solves something, whether it's a math problem or a tricky riddle, it thinks in a straight line. One thought leads to the next step by step. That works, but it also means if it takes a wrong turn early, it can get lost and never recover. Humans, on the other hand, don't always think in a straight line. We explore different options in our head, compare them, and only then decide which one makes the most sense. That flexibility is what these researchers wanted to give to large language models. They didn't just want the AI to guess. They wanted it to reason genuinely. So how do you teach a machine to do something like that? Instead of making the model bigger or feeding it endless labeled data, they came up with a framework that actually teaches the model to branch out and think in multiple directions, then pull everything back together. The model literally pauses midway, says, "Okay, time to explore," launches several independent thought paths, and once they're done, it summarizes them before continuing. It can repeat this cycle as many times as needed. That alone would be impressive, but the way they train this behavior makes it even more fascinating. Training AI to reason in parallel isn't easy. Early attempts were clunky brute force methods where you just ask the model for 10 different answers and pick the one that looks most consistent. Other methods like Tree of Thoughts or Monte Carlo research tried to be smarter, but they relied on handmade rules and external systems to steer the reasoning. None of it felt like the AI was actually learning the skill, more like it was faking it with scaffolding. And when researchers tried to directly train a model with supervised examples of parallel thinking, it fell flat. Why? Because high-quality data that shows real step-by-step parallel reasoning is almost impossible to get. Humans don't usually write down their mental branches. They only write the conclusion. And when you try to generate this data artificially, the model ends up copying the style instead of genuinely learning the strategy. A good parallel would be chess. Forcing someone to memorize grandmaster games only teaches imitation, not true understanding. So the Tencent team decided to go with reinforcement learning. The same kind of trial and error approach that made AlphaGo famous. But reinforcement learning has its own trap here. If you only reward the model for getting the right final answer, it quickly learns shortcuts. It might skip the whole branching idea altogether because why waste time if one lucky guess gets the reward? On the flip side, if you force it to always branch, it wastes effort on easy questions and slows everything down. Designing the right reward system became the central challenge. So, how did they actually pull this off? They broke the training into 3 steps. The first step was a kind of cold start. At this stage, the AI wasn't asked to solve hard problems at all. Instead, it was just learning the habit of parallel thinking, when to open a special tag, parallel, how to branch into different path sections, and how to wrap everything up with a summary. To teach it that, the team used very simple math questions from a dataset known as GSM-8K. And here's the clever move. Instead of building some giant complicated system to create examples, they just used another strong AI to generate them. Out of 7,472 practice problems, more than 83% produced valid examples of parallel reasoning. But when they tried the same trick on a tougher dataset, DAPO, the success rate crashed to 0. Not a single valid example. That test made one thing clear. If you want the AI to pick up the structure of parallel thinking, you have to start with easy problems first. Otherwise, it can't learn the basics at all. Once the model understood the structure, the next step was reinforcement learning on the same easy math problems. This time, it worked with a double signal. The AI only got rewarded if it created at least one proper parallel block and solved the problem correctly. If it skipped the format or got the answer wrong, it was penalized. This step locked in the habit, making sure the structure wasn't just for show, but actually tied to getting answers right. The third step was the real test. Now, reinforcement learning was used on harder general math problems from datasets, like at this point, the only reward was accuracy because the AI already knew the structure. What it had to figure out now was when branching out was helpful and when it just wasted time. That ability to decide adaptively is what real reasoning looks like. And the results backed it up on benchmarks like AMC Math and the tough AIM contests. The parallel R1 system beat every baseline. Average accuracy rose by about 5 percentage points compared to strong reinforcement learning models without parallel reasoning. The standout result came on AIME 25, where accuracy jumped by 9% over the baseline. That's a huge leap. What caught researchers' attention most was how the AI style of thinking shifted as training went on. Early on, it used the parallel block right at the beginning of its solutions, a kind of messy exploration, trying every angle to land on the right answer. But over time, that changed. The parallel blocks began showing up later in the process. By the end, the AI looked almost cautious. It would solve the problem mostly in one clear line, then open a parallel block near the finish just to double-check itself. During training, the AI began using parallel thinking later and later, saving it as a final check. Nobody told it to do that. It just learned on its own that being careful worked best, and that's uncomfortably close to how people learn. Now, there were actually two versions of parallel R1 tested. The first, called Seen, didn't change the model's design at all. It just learned the behavior through training. The second, Unseen, tried to keep each reasoning path completely separate by changing how the model's attention worked, so one path couldn't leak into another until the summary at the end. In theory, it sounds smarter, but here's the twist. The simpler Seen model often worked better. The structured version tended to overfit it on the easy math problems, and the tricks that worked for GSM 8K didn't carry over to harder datasets. The team had to adjust the training process for that version, skipping some stages and alternating reward signals to get it back on track. It still produced results, but it proved that sometimes giving the model more freedom works better than forcing strict rules. The reward system was another important factor. When the AI was rewarded only for accuracy, it basically ignored the parallel structure, using it just 13% of the time. When it was rewarded only for using the structure, it did the opposite, producing parallel blocks almost 80% of the time, but its performance collapsed. The best balance came from alternating rewards. Most of the time, accuracy was rewarded, but sometimes the model also got a nudge for using parallel reasoning. That setup pushed parallel usage into the 60% range and kept benchmark scores strong. And there was one more surprise. Parallel thinking didn't just boost reasoning at the output stage, it changed the whole learning process. Early on, forcing the model to branch out acted like guided exploration, keeping it from getting stuck in dead ends. Later, once the training focused only on accuracy, the model kept getting better even while using fewer parallel blocks. In other words, parallel thinking worked as a training scaffold, opening doors that standard reinforcement learning couldn't reach. So where does this leave us? For the AI research community, it's a milestone. Parallel R1 proves you can boost reasoning ability not by throwing in more data or bigger models, but by teaching smarter ways to think. It's scaling at inference time, not just in parameter count. And for everyone else, it raises a more unsettling thought. Machines are starting to use reasoning strategies that feel uncomfortably human. The story of parallel R1. So, what do you think? Drop your thoughts in the comments. I'll be reading. Don't forget to subscribe and hit the like button. Thanks for watching, and catch you in the next one.